Hello and welcome to today's lecture. We're going to start chapter 16, 16.1. We're going to talk about vector fields. So let us define vector fields. What is this field that we're talking about? Suppose D is a set in R squared, which is just a two-dimensional space plane. A vector field on R squared or two-dimensional space is a function like f that assigns to each point x and y in D a two-dimensional vector f of x and y. So the outcomes, the outputs are vectors instead of having just one real number. The best way to picture a vector field is to draw the arrow representing the vector f of x and y, which starts at point x and y. Of course, it's impossible to do this for all points. Remember that the domain is a set or subset of R squared, which includes infinitely many points. But we can gain a reasonable impression about f by doing a few representative points in D, as you can see in the following figure. So take a look at this figure here. You have function f that maps point x and y to a vector going toward this direction. Function f can take this point here and assign an arrow to this point. Another point, for example, is here, and the function f assign another arrow to this point. Point is here, function f assign another arrow to this point. So as you can see, the outcomes are not real values. These are just some vectors in two-dimensional space. In general, you can define a vector valued function this way. F takes x and y and it maps it to a vector with the first component, which might be a function of x and y, in the direction of I toward x-axis, plus the second component, it might be another function, qx and y, in the direction of y-axis. Remember that we can define a vector by just representing the components of the vector without mentioning the directions. For simplicity, you can write f function, vector valued function f, to be p in the direction of y-axis plus q in the direction of y-axis. Note that p and q are scalar functions of two variables, which are sometimes called scalar fields. Another definition, suppose E is a subset of three-dimensional space R cubed. A vector field on R cubed is a function like f that assigns to each point in three-dimensional space a vector f, x, y, and z. So as you can see, we're generalizing the idea from R squared to R cubed. A vector field f on R cubed is pictured in the following figure. We can express it in terms of component functions p, q, and r. So this vector function, vector field, is equal to scalar function p in the direction of x-axis plus second function q in the direction of y-axis plus the third function in the direction of z-axis. As with the vector functions in section 13, which you learned in Math 1C, we can define continuity of a vector field and show that function f, this vector valued function, is continuous if and only if these scalar functions or component functions are all continuous. We sometimes identify a point x, y, z with its position vector x equals to vector x, y, and z, and write f of x instead of f of x, y, and z. Or you might see it this way, f of v which is the same as f of x, y, and z. Let's go over examples to see what's going on. Vector fields are essential components of differential equations. A vector field on R squared is defined to be f of x and y. We have a nice simple function, minus y, this is your scalar function, p in the direction of x-axis plus x, which is your q, in the direction of y-axis. Question says, describe this vector valued function by sketching some of the vectors f of x and y. Very well. So we can take different points, different numbers in xy plane and evaluate the function. Take a look at this table here. Suppose your x is 1, y is 0. We plug them into the function. The first component of the function is going to be 0 because y is 0. The second component of the function is x, so it's going to be 1. The starting point is 1 and 0, and you have a vector in the direction of 0 and 1. So you can write it this way. You can say that, hey, I have 1, I have 0, and the last component, the output, is 0 and 1, which is a vector. Second point, you can take random points. It doesn't matter. You can take -1 and 0, x is -1, y is 0, and our function has -y and x, so we plug them in. Our x is -1, so the second component of the function is -1. Our y is 0, so the first component of the function is 0. So this vector valued function takes this point, -1 and 0, and maps it to a vector 0 and -1. So you can write it this way, -1 and 0. This point is mapped to a vector 0, -1. As you can see, you can plug in different points and get more vectors, which helps to visualize this function better. So 1 and 0, this is the starting point. 1 and 0 in the direction of 1 and 0, the first vector. This function takes 0 and 1, the second point, 0 and 1, and maps it to -1 and 0. So as you can see, the direction is to the left-hand side. This function takes, for example, -1 and 0, -1 and 0, and maps it to 0, -1 as a vector. So you have a little vector with a length equals to 1, the length of this vector. That's why it's smaller than the rest of these vectors, outside vectors. The length of this vector is 1, and the direction is downward. This function takes point like 0 and -1, 0 and -1, and it maps it to the vector 1 and 0. So this is the starting point, and this is the vector which represents the outcome of the function. You can take different points and actually see the direction of these vectors. This is your vector field. Gradient fields. If f is a scalar function of two variables, recall that we defined the gradient of function f to be a vector including partial derivative of f with respect to x and partial derivative of f with respect to y. So as you can see, your gradient function is actually has a vector as its outcome. Therefore, the gradient function is really just a vector field on R squared. We call it gradient vector field. As usual, if you expand the idea, if you generalize the idea to three-dimensional space, you can define vector valued function, gradient vector field to be partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of f with respect to z, in the direction of x-axis, y-axis, and z-axis. Or you can visualize this by writing it this way. So you can actually see you have the components of vector.